You're still here? Aren't you burned out yet? And you go between hope and despair, right? Oh, I can never learn all that. I'll just ask our analyst down the hall to do it. And then, but then you get excited. Oh, maybe there's a chance. There's an applied paper. Maybe there's oh no, I can't do it. And then back up again. It must be hard, right? Anyway, so I'm glad you're still here. I wish I were. I should mention one thing before I forget. One little missing data feature that was missing from the previous block is the fact that Mplus does have features related to multiple imputation. Currently, Mplus does not do multiple imputation. It doesn't generate multiply imputed data sets, but it accepts them. So we do accept multiply imputed data sets, and we have an option in Mplus that takes such data, say typically you create 5 data sets, and analyzes those data, so 5 analyses in one run, and those analysis results are summarized in the correct way, which means that the parameter estimates are averaged over the multiply imputed data sets, over the different data sets, and the standard errors are computed using that between standard error formula that came out of Don Rubin and others' work. So the estimates and standard errors are obtained for multiple imputation generated data within Mplus. That's an area where we want to develop further. For instance, create an overall model test of fit when you start off from multiply imputed data set, and adding model indirect, and adding standardized results, and adding modification indices, and adding, so the full analysis machinery should really be available even there. And so we're not quite there yet, but that's a developmental area for us. So somehow the title of the next section seems very fitting. How do you manage to stay through these kinds of 2 days? It was pretty advanced today, wasn't it? Well, it gets worse. Survival analysis is an area where I've been doing a little bit of work. I'm just a dabbler in this area, certainly not an expert. I did one paper on discrete-time survival analysis, and that's in JEBS, Journal of Educational Behavioral Statistics. You have that reference in the back, Muthen, Mason, 2005 paper. And I read a paper that I found very useful. You have these references in the back by Willett and Singer, that author couple pair out of Harvard, had a paper on discrete-time survival analysis, which can be done by tricking logistic regression programs into doing discrete-time survival analysis. And I thought about it, and I thought, well, it looks like a multivariate wide almost growth model. And so by being curious about that, I learned a little bit about survival analysis. So Mplus now has examples of how to do survival analysis, discrete time, in the user's guide. And, but also then my statistical colleague at Mplus, Tihomir Asparohov, has done some fantastic work on the continuous time aspects of survival, and brought that also into the latent variable framework, borrowing some ideas and some inspiration from a former postdoc of mine, Klaus Larsen, who was at UCLA for a couple of years and is now back in Denmark. Anyway, discrete time survival and continuous time survival can be used on the same kind of data, but typically discrete time corresponds to more infrequent measurements, like grades, for instance. Grade 7, 8, 9, 10 would be an example. So a fairly limited number of time periods. Continuous time, on the other hand, frequent measurements and a larger number of time points is what you typically see. Discrete time survival analysis, I describe that as the more easily understandable survival analysis, and some people think it's the other way around. Other terms for that kind of analysis is event history analysis, time to event. And the sociological statistician Paul Allison, who's done a lot of interesting missing data work, he has also done work on discrete time survival analysis. Here's a Singer and Willett paper. And Jerome Vermont, the Dutch methodologist, has written a book from his dissertation, which also includes such analyses. So the setting for the discrete time survival analysis that I've been part of looking at is discrete time periods and a non-repeatable event. So something that only happens once, starting using drugs, for instance, or being thrown out of school. And you talk about uncensored and censored individuals. Censored individuals is correspond to the study has ended without you knowing or without you seeing whether the event has happened. It may happen right after the study ends, but you don't know it. Uncensored individuals are those where you see the event happening. But you have the same situation as in growth modeling with time invariant and time varying covariates. And the aim really is to estimate time to event. Survival curves and hazard probabilities are ways to describe the influence of covariates on the time to a certain event. There are many generalized models in this area. You can certainly bring in multiple latent classes, but it is tough to do that. There is a precursor to that in the survival literature. You talk about long-term survivors who die for other reasons than the particular event that you're interested in, the particular cause that you're interested in. What we have been successful, Catherine Mason and I, is doing mixture modeling, growth mixture modeling, followed by a survival analysis. So latent classes for development are predictors, latent predictors of survival. And that's part of the Jebs paper. Earlier today we talked about survival followed by growth or growth mixture modeling. That was the Albert and Shih idea, and that's less well developed. But I think Catherine wants to try to contribute to that. So anyway, we can talk through some applications here. Actually, with we're right in the middle of it. That is geographically. We are in Baltimore, right? This is Baltimore. This is Friday. Yeah, it's Baltimore. So we have Hopkins data, aggressive disruptive behavior related to school removal, which is a fine euphemism for being kicked out of your class. So you have discrete time survival analysis. Consider this single non-repeatable event. And I should say there are many flavors of survival analysis. It can be repeatable events. It can be multiple processes, competing risk models, all kinds of variations on the theme. And you should know that there is a fine dissertation by Catherine Mason sitting on the website of Mplus, where she lays out survival analysis very nicely in various forms and shapes, and she has other papers there too on that website. And this is an interesting feature. I haven't seen that before. Anyway, we're going to introduce our favorite U variables. Again, you know, U variables, they pop out at the end of the day, and they should warn you now. The warning sign is going to be complicated. They came up yesterday afternoon in the categorical growth, binary growth schizophrenia context. They came up in the missing data section for missing data indicators. Here they are event history indicators. So we are going to work with event history information in entered into a vector U where R is the maximum value of J sub I over all. You know, what does this mean? Let's see. Let's take an example and calm down. Let's say that you have 5 grades. So here's your vector observation. And this is grade 1, 2, 3, 4, 5. Here is an individual who is censored, which means that the event did not happen before the study ended. So the 0, 0, 0, 0 means it didn't happen. The event did not happen. This person was kept in school, behaved well, I guess. An individual who experiences the event in the 4th period, at the 4th time point, that individual gets a 1 there. And the convention here to put discrete time survival analysis into this multivariate wide approach in Mplus is that once the event has happened, you code the U for the next period as missing 999. So as soon as a 1 has occurred, there will be 999 thereafter. And if he drops out, he's a missing in the regular sense, he gets 999. But scoring that way and formulating a model like this, we feel much better already, right? We have a model diagram, we know what to do with it. And the idea is that the Willett and Singer, who wrote that Jebs paper I was inspired by, they laid out the log likelihood for how to do discrete time survival analysis. And very much in line with the 2-part JASA paper, you can create data, the U variables in this case, so that when you analyze them by the right likelihood. So for instance, for the 2-part model, for those who are statistically interested, Olson and Schaefer never laid out the 2-part model like I did with continuous and binary. They never formulated that way. But you can formulate your data that way and then do the parallel process analysis, and you will be working with the same likelihood. So for the statisticians, they know what I mean, that once you have the right likelihood, you're doing it well. But the advantage here is that you come down to a familiar framework. You have 5 U's, binary U's, and you have a covariate X. And the U's are scored like on the right here. And then you formulate a probability model for the U's, just like we did for yesterday afternoon, categorical response. And if you look at just the left and the right, probability that you experience the event for individual I in time period J, then it is a logistic regression, right? This expression reveals itself as a logistic regression function, as a function of X, with a certain intercept that we call a threshold, tau, and a certain slope that we call kappa. And that is then the probability of experiencing the event in time period J, given that it was not experienced prior to J. That's what this convoluted expression says. That's the hazard. And a proportional odds assumption is obtained by dropping the J subscript for K. This is saying that a proportional odds assumption in the discrete time analysis says that the influence of X is the same at all the different time points. But essentially, think of X as a risk factor, and when it increases the hazard, that is the risk for experiencing this adverse event. From these probabilities, which is like a categorical variable model, you can create a survival function the probability that you haven't experienced the event up to a certain point, and a likelihood, and we don't want to get into this, but this is how the likelihood expression is formulated, and a hazard plot. We're going to take a look at that for an example. School removal data, Hopkins data, and let's look at males and females over different grades, 1 through 7. And there are 200 males here, and we ask, among those 200, how many were removed from school in grade 1? 4 out of 200. So the sample hazard is 2%. Of the remaining 196 individuals who are then at risk for being removed for the first time, 5 were removed in grade 2, given the hazard 0.03. Of the remaining 191, 7 were removed in grade 3. So you have these hazard probabilities, you know, that we have the categorical model expression for here. Wow, that's interesting. 215. Sorry. It's a computer difference. Okay. No, that's all right. We don't. So this is a logistic model, and what we're observing, this is the model probabilities, and here are the sample probabilities that we want to try to fit by our model. So it looks like the hazard is fairly constant, a little bit increasing over the grades, and compared to females, males are more at hazard for being removed from school. So you can therefore plot the hazard estimates corresponding to those calculations. We're going to do it for males, solid line, and females, broken line. Males below the mean and above the mean, one standard deviation of TOCA 1F, which we now know is the aggressive disruptive score in fall of first grade before the intervention started. So you have the males one standard deviation below the mean on TOCA, and the males one standard deviation above. So the more aggressive you were in the fall of first grade, the more likely you are to be removed from school. These are the males, and here are the females. Both lines lie below. This is the sample expressions. We haven't modeled yet. The corresponding survival plot is probability that this hasn't happened yet by a certain grade, that you survived and don't get thrown out of school. Now, there are lots of models you can consider here. We drew this model at first. U is a box, an oblong box, a rectangle, which means that there's several U's. It's a series of U's over time, over these 7 grades, for instance. And X is our risk factors, like aggressive behavior, TOCA in the fall of first grade, influencing the hazards. On the right, you have this proportional odds assumption, namely that a certain risk variable X has the same influence on the hazards of the events at all the time points. One way of doing that is to introduce a factor F continuous variable influencing U with equal unit slopes. Then X, gets channeled through and gets multiplied by 1. That is, this little slope is used for all of those time points. It's just a little trick. Instead, you could have done it over on the left, holding the slopes equal. But it's very pedagogical to go through F, because you could then imagine that you have a residual for F. That residual is called a frailty. So we're trying to bring in all these concepts. That is, you take a bunch of X's to try to say which factor are risk factors for a bad behavior, like death, for instance. And even though you collect all kinds of X's that you can get your hands on, there are still differences between people that influence their probability of dying. And that is then those differences that are not measured by X are captured by a residual, as usual in statistics, in regression. So when that residual is part of the model, you have a frailty model. And it's very interesting, as soon as you try to bring that residual in there and estimate its variance, the model is harder to estimate. So the standard discrete time survival model does not have that. It has f on x, but the residual variance of f is fixed at 0. And then f by u1 up to u7. So we'll see examples of that setup. At the bottom of a couple of variations that we used in the Jeb's paper, Muthen and Mason, 2005, where you have a latent class variable behind the frailty. And, well, we focus on this model actually. We have early development, grades 1 to 3 development of aggressive disruptive behavior with its growth factors. And there is a growth mixture. So we are looking at different classes of individuals' development and then predicting the frailty for the events of being thrown out of school as a function of the latent categorical latent class predictor. So that's sort of a summary of our paper. Input is very simple. This input on slide 221 corresponds to the model at top right, the top right model without the residual for f. So you say f by u1 through u7 at 1, and f on a bunch of covariates, and the residual variance for f at 0 is fixed. So you have the classic model. And you declare the use as categorical, and you have already formed the use in that 0, 1, 0, 0, 0, 0, 0, 1, 9, 9, 9 fashion that we talked about. This is Hopkins data. Again, you don't get an overall test of model fit here. You get thresholds for use, which have to do with the hazard probabilities at the different time points. And the way we're not going to have energy to go into the details, so it suffices to say when the lower thresholds correspond to higher hazards. Lower thresholds correspond to higher hazard, higher risk of experiencing the adverse event. And what we're interested in is really f on these different background variables. And for instance, if you look at y1 down here, y1 is the aggressive disruptive TOCA score in the fall of first grade. And it has a positive influence on f, meaning that the more highly aggressive the child was in the fall of first grade, the higher the probability of dropping out. Not dropping out, being removed from school. Significantly so, which is also what we saw in the sample plots that we were doing. So y1 is TOCA in the fall of first grade. CAV TOCA, as we all know, is class average TOCA. Class average TOCA, it's interesting, negative effect. So I think that should be interpreted as if you're aggressive in a highly aggressive, you have less of a risk of being thrown out of school if you're being aggressive in a class that's highly aggressive. I guess you won't be noticed as much. But I'm not sure about that. Class average lunch says what's the average poverty of that class. The higher poverty for that classroom is among the students, the higher you're at risk for being removed from school. So that's very easy to do this analysis. Here we're talking about, on slide 274, all kinds of complex extensions which we don't want to talk about right now. And that's two-class discrete time survival analysis. which we don't talk about, but you have the output there. Instead, I want to give you some pointers then. Here's Paul Allison's 84 opus, Event History Analysis. Here's an interesting Catherine Mason article or chapter in a very interesting book, sort of a sleeper book. It doesn't get advertised. It's one of those books that we print on demand, but it's a very nice book. Greg Hancock and Karen Samuelson organized a conference on latent class mixture modeling some years ago at University of Maryland. Had the energy to put together an edited book, Advances in Latent Variable Mixture Modeling. So Catherine has a chapter there on modeling event occurrence where you have a measurement error in the event recording. You're not quite sure if the event happened or not. I guess that's clear if your school removed, but there are other applications where you're not, for instance, if you're saying, talking about the first time you started drinking, what should that mean? Is that a sip with your parents, a drink on your own, regular drinking, or what? So you can imagine that in practical situation there's a measurement error in there. She has a very interesting chapter on what to do in that case, in this chapter. If you go to the Mplus website, under Papers and Survival Analysis, you will find this. And you will find instructions for how to purchase this book, which has a lot of interesting variable mixture models. You may want to do that before you come to, did I mention Ann Arbor? Okay, here's the Muthen and Mason paper. Technical in part, but with two concrete applications. One application having to do with incarceration. A classic example also used by Paul Allison, actually an intervention. And the intervention has an effect on the recidivism, which means, you know, coming back to prison, basically. So the time to coming back to prison is affected by the intervention. Singer and Willett, clever with words. It's about time. That's the paper I was inspired by. Very pedagogical about how, if you're interested in education, how teachers get tired of being teachers. Nice application. And they have a very good book. Again, we mentioned that yesterday. The ratio of words per formulas is high and nice for those who don't like formulas as much. And then Vermont's much more technical book. Now, continuous time survival. Some of you connect that with Cox regression. And Cox regression is part of Mplus, but in a much more general framework than regular settings. Let me tell you about it. So, first of all, we have to penetrate this formula page. I'm sorry. I know it's late, but it's not that many. You know, it's only two equations. So T0 is time to events such as time to death. How long does it take for people in this study? When do they die? I is, does it say I? It's a wobbly screen, so time of sensory. And I'll tell you what that means. I guess I've alluded to that. When you no longer observe the person is the time of censoring. The person may or may not have died before you no longer see that person. The survival variable T and the censoring indicator C are defined by T is the minimum of T0 and I. So the minimum of either they die or they are no longer observed in the study. So there's a minimum of that, that's T, but then you don't, T doesn't tell you from that if the person is dead or not, and you really want to know. It's sort of morbid story. C is equal to 1 when you have censoring, that is, if T0, the death, happens after they have left the study, that is right censoring. You know, if death happens after they have left the study, then censoring is equal to 1. Otherwise, it's 0. And here, then, the punchline. Everybody can understand this. For example, formulas 1 and 2, this is a little brain teaser, but easy. C equals 1 implies T equals I, the time the individual leaves a sample. Why? C equals 1 implies that T0 is greater than I, which implies that I is the smallest of the two, which implies that T is equal to I, which is the time the individual leaves the sample. So it was doable, right? Yeah, right. You probably snoozed through that. Anyway, so proportional hazard model is a common survival, continuous time survival model. It specifies that the hazard function that we talked about is proportional to the baseline hazard, which is baseline hazard is sort of an intercept hazard when the covariates are at 0, sort of an intercept hazard. The baseline hazard is h for time point t. Baseline hazard is lambda sub t, lambda parenthesis t, and the function of the x-axis is e to the power of the slopes times the x. So here's the regression part. The baseline is lambda, and the other part is x beta x. And there are really two proportional hazard models, at least, that you can consider. One is a non-parametric shape for the baseline hazard function. That's what's called Cox regression. So that's one of the possibilities you have in Mplus, standard Cox regression. And the other is a parametric model for the baseline function, a parametric PH, proportional hazard model. And both options are available in Mplus. And the Cox regression can be done with all kinds of twists in Mplus. Here is the most straightforward approach. This is straight out of the user's guide. And you have the names are T, X, and time of censoring, TC. You know, we talked about T, we talked about C on the formula page. Here they appear again. T is T. TC is what we call C, time of censoring. So the survival variable, the dependent variable, is T. And time censored is denoted TC. 0 for not censored, 1 for right censored. Just like on the little formula page. Base hazard is off, which means that we don't model it, and we have Cox regression. And then the model is very simple. We just say T on X. T on X is the path diagram. Now, the thing is that some of the X's can then be latent. Could be continuous latent factors or random effects or categorical latent variables and random effects. And various kinds of variations on that theme. And that's due to the skillful thinking and programming of Tihomir Asparuhov at Mplus. Here's what data, continuous time data, look like. We have T, X, and C. C is the TC that we have here. So this is the time variable. And again, we agreed that time is either time of censoring or time of death, right? We did agree on that. So here's the X variable, and here is the censoring indicator. Censoring indicator C. So for instance, for the third line here, a censoring indicator is 0, which says that the event T0 is happened, the death happened before the person got lost in the study. So 1.219 is actually the time of death here. So C equals 0 is a serious case, whereas the first line here says that T0 is greater than I. They die after they leave the study, but they leave the study at time 7.3. So this is what the data look like. could be of interest when you apply these techniques to real data to try both continuous time and discrete time survival. And I wanted to help you with going back and forth between those type of data representation. Here I have just one way of going, translating continuous time survival data to discrete survival data, but if you want to, we can provide you with the opposite direction. So you have here continuous time survival data, which looks like on the right screen, and you want to create categorical variables for discrete time survival. And here's how you do it. And the explanation for this is in define, and the explanation is that if u1 equals 0, if u1, the event history indicator is 0, the event has not happened. If c equals 1, that is censoring time is between 0 and 2. And u equals 1 if the person died then in this time interval between 0 and 2. And then for the next u2 period, you create u2 down here. u2 is missing either because u1 equals 1 or because u1 equals 0 is equals 1. I don't expect you to follow these now when you're tired, and there's a lot happening through these days. But I want you to have those pages, so if you want to go between data that you have analyzed by Cox regression, perhaps in SAS or some other favorite program, you know how you could either analyze it by Cox regression in Mplus or move it over to discrete time survival analysis in Mplus, and you get a further understanding of how those two data representations connect. And we come to this page, 240. And further readings. This paper is the summary effort of the Mplus development for the general latent variable framework inclusion of continuous time survival. It was presented at the statistical meeting in Seattle, August 2006, and it's ASA section proceedings. Sits on the Mplus website under survival analysis. It's technical, but it's quite exciting about the possibilities that can be realized. Some of it is inspired by and extending the work by Klaus Larsen. Folks, I'm sad to say, but you have survived. Well, I'm not sad about that, but that's the end. We are at page 241. So that's the end of our 2 days together. Before we take the question and answer session, I would like to say that I've enjoyed all your good questions. And may you go out and do great analyses now. Tell me about your successes. And we can put them into sample sections in future versions of it. So maybe I'll see you at Ann Arbor. And with that, let's start the question and answer session. The final one. Yes?
I think you said this at the beginning, but can you restate the work of continuous time survival analysis and then switching to the discrete time? You illustrated on that.
Yeah, so the question is, why would you do a continuous time versus discrete time survival analysis? I think it really depends on the situation. If your data are more like at the top or more like at the bottom. If you really want to look at the details of timing of the event and have a lot of detailed information about it, it's more natural perhaps to do continuous time survival analysis. Otherwise, it may be a little unnatural to do continuous time survival analysis on very sparse data like the Hopkins aggression example that I mentioned. But it should give very similar results. I think both are published. That's our bottom line, right? Okay. Well, yes?
Yeah, page 202. Do you have a code for those non-ignorable models? So we can use it. You want us to use it?
For this, code for this? You know, I might have that. If you send me an email, I probably can dig out where I did that, made that effort. It's not on our website, but it's on my computer somewhere. You have more energy, don't you? Yeah, but the train and the plane and the bus is leaving, right? All right. A final question. Nick, you have a question? Shouldn't we all thank Nick for arranging these? Nick and his assistants and associates put in a lot of effort to make this possible and sponsor this at a low fee. So we're thankful for that. So great. Come back. See you in Michigan.